Now that we know what our mathematical model is, it's a boundary value problem we were looking at, let's consider how that mathematical model is solved approximately using the finite element method, and what are the errors introduced in the process. If I go back to my framework of what's inside the black box, I'm moving from talking about the mathematical model to talking about the numerical solution strategy used to solve it to get displacements at selected points. So the numerical solution strategy uses the finite element method. So you divide the domain into elements and nodes. And this shows an example of that. And so you would call this a mesh. And each of these little volumes is called an element. And the corners would be the nodes. So these corners, for instance, and also on the inside. You could also have mid-side nodes, as we will see, but let's ignore that for now. And you say, hey, it's really hard to determine the displacements everywhere. So I will, we'll determine the displacements only at selected points, which are these nodes that I marked out over here. So a big jump here from finding the displacements everywhere, finding unknown functions, to finding discrete values. And that idea is called discretization. And these ideas are familiar to some of you. For some others, it might be new. So this is just kind of a quick and dirty overview of the big ideas. And you can use a polynomial interpolation to relate u, v, and w at any point within an element to the nodal displacements. So if I want to know the nodal displacement, say at this point, I would use an interpolation of these four values. You can think of the interpolation as a weighted average using shape functions for those who have seen that idea. So again, another big idea here, this element by element polynomial interpolation. And if I go to a 2D analogy, this might be easier to understand. And this I've taken from my big ideas in finite element analysis in my free EDX course, Hands-on Introduction to Engineering Simulation. So you might want to take a look at that if you want to know more about this. So if in a 2D analogy, your domain might be a rectangle, you're doing some, you want to find displacements of a plate, and you would divide it into little chunks, which could be rectangles, and I've highlighted an element here. I've highlighted the nodes. So how do we find nodal displacements? Because that's what we have reduced the problem to. We take our boundary value problem and we derive a set of algebraic equations in the nodal displacements using our element by element polynomial interpolation for u, v, w. So, and in the process, you're introducing an error, and these algebraic equations, as I discussed elsewhere, will relate the nodal displacement only to its neighbors. So in the 2D analogy, if I want to know if I derive the algebraic equation for, over here, it would involve displacements only at the neighboring values. And this is the set of algebraic equations is usually written using the stiffness matrix, which you might have seen elsewhere, KD equal to F. So D is is a vector containing all these displacement values. At each node, we have 3 displacements for a 3D problem. And K will be a sparse matrix because of this property that, each algebraic equation will involve only the neighboring values. And then once we have the set of algebraic equations, we can use ANSYS to invert it to get the nodal displacements. And then from nodal displacements, we can interpolate to find the displacements everywhere. And using that interpolation, we can differentiate it to find the strains and then the stresses. And that's post-processing. So how do we reduce the error then in the finite element solution? The error is introduced in going from a boundary value problem, differential equations, to algebraic equations. And and we see that, we do that using the element by element polynomial interpolation. I won't get into the details of how we do that. You can do that using the weak form or the principle of virtual work. And again, you can go to the big ideas in finite element analysis to see more details of that. But this shows us that the better our polynomial interpolation, less is the error. And so how do we get the polynomial interpolation to be better? Because in that, as the polynomial interpolation gets better, the finite element solution will tend to the exact solution. We can increase the number of elements. So if that's our original mesh in the 2D analogy, and that's a refined mesh, intuitively, we know that this is better. So for instance, if I'm using an interpolation for a value there, in this case, it would involve these values, these nodal values. If I take the same location, it would involve these 4 values, which are closer. And intuitively, that's better because we're using these values only to interpolate over a smaller area. But there's another way that's less intuitive to get the interpolation to be better, which is to increase the order of the polynomial. So for instance, if we also now use that as a node, so we determine displacements not only over here, but also in the middle, which in my drawing it doesn't look in the middle, but typically it's in the middle. Then if I'm interpolating along this line, I'm going to use 3 values, so I can do a better fit for whatever variation I have, as opposed to using just 2 values. A quadratic interpolation is better than a linear interpolation. It's a curve fit, except that you don't know these values. So you have to find those values by inverting the stiffness matrix. So we will get back to these ideas when we are in ANSYS, but that gives you a quick and dirty explanation for the numerical solution strategy used to solve our boundary value problem.